Hello everyone and welcome to the channel. This is Nuruluda and I am a verified educator at an academy. I just wanted to inform you guys that I am teaching live on an Academy Plus. So if you guys are interested in attending those classes, if you guys are interested in learning from me live, so you can take an Academy Plus subscription and join my classes over there. The classes on an Academy Plus are more organized for CSI net preparation and they are more focused towards the exam, right? So if you are interested in that, you can subscribe for an Academy Plus. The links are given in the description. Let's continue with the video. Hey guys, hello everyone and welcome to the channel. So in this video I'm going to talk about perturbation theorem, and as you all know that this particular perturbation theorem is actually used for like system having single particle, right? So why we are using this perturbation theorem and all? So first of all I'll just want to explain you that thing. So see, we actually solve our Schrodinger wave equation or Schrodinger equation, and the need of that Schrodinger equation is to obtain energy for different systems, right? So we have different systems, like let's say we have one dimensional like particle in a one dimension, two dimension or three dimension box. Then we have simple harmonic oscillator as well. Then we have hydrogen atom problem. So these kind of like to find out energy of these systems, we use Schrodinger equation to solve, right? And when we solve a particular Schrodinger equation, we get certain amount of energy with that equation. Now that energy which you have calculated, that means our calculated energy, it may be equal to your like exact energy which is corresponding to that system, or it may be like it may be different from that, right? And in most of the cases it's not actually equal to that. It's quite different, or it's quite like it's not equal to that, right? So the energy which you have calculated from the Schrodinger equation, like it is not equal to the exact energy which is corresponding to that particular system. So to obtain that thing, to obtain more and more exact energy value, or to obtain energy which is more near to the exact energy value, we use different methods. Those methods are called approximate methods. Okay, so these are your approximate methods. So basically we have two kind of approximate methods. Either you use perturbation theorem, okay, perturbation theorem, or you use variation theorem. Okay, so as I have already explained about variation theorem in my one of the video, like which I have just uploaded few days back. So here is the link for that. You can watch that video over here. So in the variation theorem we have more than one particles, right? So over there we have more than one particles, and for perturbation theorem we have a single particle system. So for that we generally use our perturbation theorem to solve it out. Now yeah, so we'll talk about this perturbation theorem in more detail in this particular video. So let's start with that. Right, so this is what your perturbation theorem is. Okay, so it's an approximate method and it is used to rectify the energy difference in the real part and the calculated part, right? Now this correction, this perturbation theorem, what we do actually in perturbation theorem, we try to correct our energy term. We do certain kind of correction in that, and that's what we call first order and second order correction. Okay, so there are basically two kind of correction which are being done in a perturbation, like to find out the exact energy, or to find out the more appropriate energy of a given system. So those corrections are like first order and second order correction. So we know that from the Schrodinger wave equation, what we have, this is the simplest form of Schrodinger equation, that is h psi naught is equals to E psi, where h is your Hamiltonian, right? And psi is, let's say it's a wave function on which it's we are applying this Hamiltonian operator, and we are getting a eigen function, eigen value of it, that is the energy of the system, and this is psi naught. So this is what the basic or the simplest form of your Schrodinger equation tells you. Now the real part which you will solve, or which you will get, it may have a Hamiltonian that will be having the value for the exact part, that means for the real part, and also it will also have some error in that. Okay, so this is what the difference is, or this is what the thing which we are missing out in that. Okay, so that's what it means. So this means that there is there is need of correcting this term in order to reach up to, like, in order to make h dash, which we are like, h dash is the value which we are correcting and h naught is the real value. Okay, so in order to reach the real value we need to do certain correction, that is your delta h. Okay, so that's what it is. So the same kind of perturbed part, or the or the error part will be there in your energy also, and also in the wave function. So these equations, these three equations tells you whatever I have taught, whatever I have told you in the theory part, that there is certain like certain difference in the calculated part from the real part, and that difference is actually this delta H in Hamiltonian, delta E in energy, and delta psi in your wave function. So we try to we try to correct these things only, but the only correction which we can do over here is the energy correction, and that energy correction we'll try to do it, and we'll try to obtain our energy, because the sole motive of solving all these things is to obtain exact energy, okay, to obtain the energy which is very near to the exact value. To obtain that energy, we do certain correction to nullify this factor, that is delta E. Okay, so now the kind of correction which we generally do, that is your first order energy correction and your second order energy correction. So let's talk about our first order energy correction first. So the equation for your first order energy correction is given by this, that is delta E dash n is equals to psi star n delta H psi n d tau. Okay, so your n is the energy level for which you are correcting it. So n is the particular energy level for which you are correcting that particular thing. So let's say if you are trying to find out equation for the first order energy correction, then it will be like E dash 1 is equals to psi 1 star delta H psi d tau. D tau is for the 3 dimension, and d tau is nothing but like d tau for a 3 dimension, you can write it like this: dx, dy, and dz. If you are trying to do in a single dimension, then your dx will be only there, rest of the terms will not be there. Okay, so d tau you all know, right? And yeah, so these are the things. Okay, so n is the energy level. So this is how your first order energy correction equation looks like. So this is the equation. I will tell you the use also of it, so don't worry about that. Now there is something to note down, is that for a simple harmonic oscillator, if the perturbed part is odd, okay, if the given perturbed part is odd, then the energy correction will be zero. So always remember this thing, that for a simple harmonic oscillator, if you are given with the perturbed part, and if it is odd, in like if its power is odd, then your energy correction will be zero over there. Let's try to do some questions based upon this, and then let's try to understand second order energy correction. Right, so let's talk about this particular question. And this question was asked in your CSIR December 2017. Okay, so, and it was asked for 4 marks. So let's try to solve it up. The question says that for a one dimension quantum harmonic oscillator, right? So for a quantum harmonic oscillator, the perturbed is perturbed by a potential of lambda x cube. The first order correction of the energy for the ground state is, so they are asking you the value of delta E1, that means the first order energy correction, and you all know what is the formula. So it's like yeah, so we have this psi star like H, and sorry, it's delta H and then psi, right, d tau. So here this delta H is the perturbed part actually. So here the perturbed part is given by lambda x cube. Now I have already told you that if your perturbed part is odd, okay, odd means what? As you can see over here, it's lambda x cube, means the power given over here is odd power, right? So the term will become odd. So the perturbed part becomes odd. So you can generalize it like your perturbed part should have a odd power. Okay, so like that you can understand. And what it says, that if the perturbed part has a power odd, and if the system is what? System is your simple harmonic oscillator or a harmonic oscillator. In that case, your first order energy correction, your delta E1 means first order energy correction, is always equals to 0. Okay, so it's a direct question for what I have told you. So you can just directly answer it as option number 3. So option 3 becomes your correct choice without any solution, without doing anything. This becomes your first choice, right? A similar question was asked in your, I think in December 2015 it was asked, or I think December 2014, I don't remember the year exactly, but over there the perturbed part was given like lambda x. Okay, so the perturbed part was lambda x over there. Same conditions were given, like it was given as a simple harmonic oscillator given to you as a system, and it was asked that what is the first order energy correction. So over there as well your answer would be 0, right? Now let's take a question where the system is not a simple harmonic oscillator, where the system is something different. So let's try to see over there that how we can find out our first order energy correction in that case. Alright, so let's try to solve this particular question. The question says that the first order correction to the energy of the ground state of particle in one dimension box, that is from 0 to L due to the perturbed part lambda x is okay. So now you have to be very careful. Don't just like in the option you will also get 0 as the option. So don't just look upon to the perturbed part and see that power is odd, so the answer will be 0. It won't be like that. Why? Because the condition over here or the system over here is the particle in one dimension box, not the simple harmonic oscillator. Okay, so be very careful here. You have to solve it and you have to find out. So let's try to do it. So the energy correction for the first order, so we'll write at E1, and for the ground state, that's why it will be 1. Okay, so it will be equal to what? It will be equal to 0 to L, because that's the limit you are given with. You have psi star, okay, then you have like the perturbed part, that is your lambda x, okay, and then your psi naught, and instead of d tau we will be writing dx. Why? Because we are doing it in one dimension, so it will be dx over here. So now lambda is a constant, so it will come outside because it's a scalar quantity, so it will come outside. It's a 0 to L psi star x psi naught dx. So that's what you will get, right? Now what you have to do is you should know that what should be the value of your wave function in your for a particle in one dimension box, right? So just try to put it up over here. So it will be like lambda 0 to L, and the value of psi star is what? So your psi is basically given by this, that is psi is equals to under root 2 by L sine n pi x by L, right? So this is the value of psi, so just put it over here. So psi star and psi both will be same, so I'll just write it down over here. So it will be right, so this will be the equation now. So just multiply and take out this 2 by L outside, okay? So it will be like lambda into 2 by L, because under root 2 by L and under root 2 by L will become 2 by L, so that will come outside. And in the integral part you will be having 0 to L, you will be having x, along with that you will be having sine square n pi x by L, okay? So n pi x by L and dx, so that's what your value will be. So now you have to integrate this thing. Now those who are from maths background, they can solve it, they know how to use calculus and solve it out. For those who are not from the maths background, those who don't know how to integrate this term, I'll just tell you a shortcut trick. So remember this thing that if you are integrating from 0 to a and the function is like x sine square n pi x by a, okay, just remember that whatever the function is, like if it is 0.0 to a, then it should be a in the denominator and there should be n pi x, okay, and dx, then the answer will be a square by 4, right? So the similar way, if you will just match these two things, this is the thing which I have said you to remember, okay, this thing. And if you will see in the equation which we have just got, we have in the place of a we have L, right? So in the place of this much integral, what we are going to get is this. So lambda is already there, 2 by L is already there, and at the place of that integral we are going to get L square by 4. Understood where this L square by 4 came? Instead of a we have to write L, because we have L over here instead of a. It's a general way of just telling you guys, so just remember this. So just when you solve this thing, you are going to get lambda L by 2. So this will be the answer, okay? So this will be the first order correction to the energy in the ground state of particle in one dimension box. Okay, so now let's try to understand the second order correction. So let's try to understand the second order energy correction now. So this second order energy correction is much easier as compared to your first order energy correction. You might have seen in the last problem I have solved a little bit of calculus for the first order energy correction, but in the second order energy correction you don't have to solve. The questions won't be asked in that way, and like it is quite more easier, and especially for those who are not from mathematics background, for them this second order energy correction becomes more easier. Why? Because here you just have to be very careful with the terms and all, and you don't have to do a lot of maths over here, okay? So you can see it's a equation given for second order energy correction, okay? So this delta E n signifies that you are trying to do energy correction for nth order or for the nth energy level. 2 signifies that it's a second order energy correction, is equals to sigma, right? So sigma basically tells you that you have to sum it up, like you have to add the terms. n not equal to m. So n and m should not be equal. What is n and m? I will tell you both of them. So actually, how is it written? Just first of all, pay attention over here. So it's psi m delta h psi n whole square, okay, and in the denominator you have en minus em, okay. So where this m and n are two different energy levels, so n and m are energy levels. So what happens actually, that n is the energy level, okay. So I'll just write it down over here. So n is the energy. So remember, n will be the energy level for which you are doing the energy correction. What is m then? So m is the all possible energy levels from where the transition can happen, okay. So m is the other energy levels from where the transitions can happen. So just remember this thing, that n and m are both different, okay. And you have to be very careful with the position of m and n. So always remember that in the numerator you have psi m and delta h and then psi n, but in the denominator you have en first and then em afterwards, okay. So m is like written later in the denominator over here. Fine. So for the ground state, always remember that the ground state start from 1, okay. So n will be equal to 1 for the ground state. Your n will be equal to 1. And what will be m then? So m can be equal to 2. So n and m cannot be equal, right? So m cannot be equal to 1. It will start from 2, 3, 4 and so on, okay. So if let's say m is equals to 2, in that way your equation will become psi 2 delta h psi 1 whole square divided by e1 minus e2, right? Plus, because it's a sigma sign, so you have to add the next term. So plus, then you have like m is equals to 3. So psi 3 delta h psi 1. Why? Because n is 1. So you have to be very careful with that. Divided by e1 minus e3. And for the next term, it will be what? It will be psi 4 delta h psi 1 divided by e1 minus e4. So like that. Because it will go like that. In the simplified way, you can write it in this form, that is delta E12 is equals to this thing, this delta H, you can write it because it's from 2 to 1. So you can write it like delta H21. Okay, so that means between psi 2 and psi 1. So that is delta 2H1. Remember this thing I have taught in a variation theorem also. So it's from there only. Okay, so yeah, so it's H21 and in the denominator it's E1 minus E2. Then you have H31 divided by E1 minus E3. Remember, if it is 2 1, so 1 minus 2. If it is 3 1, then 1 minus 3. The next one will be delta H41 and E1 minus E4. So like that it will be. Understood? So this is the only thing which you need to know about your second order energy correction. That's all. Okay, that's all for the simplest like explanation of this second order energy correction. We'll try to see that whatever we have studied, is it helpful? Can we solve questions related to that? Let's try to do some questions. Right, so we'll take this question. It was asked in CSR December 2015 exam and it was asked for 4 marks, right? And the question says that a certain 2-level system, that means we have 2 different levels in that, 2 energy levels are there, E1 and E2, where E1 is lesser than E2. That means E1 is of lower energy and E2 is of higher energy. With normalized wave functions psi 1 and, so here you have phi, okay, so you have phi 1 and phi 2. Doesn't matter whether it is psi or phi, those are representing your wave functions. Now in the presence of a perturbation V, okay, so here perturbation is given as V. Now remember where we have studied in the form of H, right? The perturbation we have studied in the form of H, but here it is given in the form of V. Doesn't matter, you just have to replace H with V, that's all. The second order correction to the energy of the first state, okay, you have to tell for the first state. So remember, so I'm just going to write down the energy term over here, which we have just studied. So E2, and that means second order energy correction for nth order or the nth energy level was given by this, that is psi, we were having psi n, psi m, right? And then we were having H, then psi n square, and in the denominator we were having En minus En. Okay, so this was what we have studied right now. Now for this particular question we have n is equals to 1. Why? Because we have to find out for the first order. So for the first state, so n is equals to 1. And what will be m then? M will be equal to 2. Why? Because you just have 2 energy states and you are talking about one of them, like you have to find out for one of them. So the transition will be done from the second one, right? So m will be equal to 2, and h over here is represented by v. So that's all you have to do. So just what will be the answer then? So just write down them. So it will be like E1 to second order energy correction for the first energy level is equals to, okay, so instead of psi we have phi over here. So I'm just going to write down in the form of phi. So it will be what? It will be phi m means phi 2. Then we have v. Then we have phi 1. And then average value of that, square of that. And in the denominator you will be having what? E1 minus E2. Right? So this is what you are going to get. Now if you just match this up with the options given over here, it won't match with anybody, right? You will get the denominator matched with option C, but the numerator won't match over here. Try to pay attention to the options given to you. In the third option you have mod also, right? You have mod given to you. Mod means you can, like, the negative value is also become, that will also become positive one. So if you put it in the modulus form, so in that case your psi 1 and psi 2 can interchange their position. Okay, so in the place of, if you just place modulus over here, so you can write it in the form of this, that is phi 1 v phi 2, right, square, and divided by E1 minus E2. So now your answer can be your option number 3, right? So you can easily say that your option number 3, the only thing which they have done for this particular question is they have put modulus just to confuse you, just to make just to make you guys confused. But always remember, the energy term over here in the denominator should match, and you should have a square in the numerator, right? So that is only satisfied with your option number 3. So that's how your option 3 becomes your correct choice, and that's how you can easily score 4 marks from this particular part. Okay, let's take another question and try to solve it. Okay, so let's take this particular question. It was asked in your CSIR June 2018, right? And the question says that okay, so the question was for 4 marks. Okay, the question says that which of the following statement on the ground state perturbation theory involving the zeroth order energy, this, first order energy correction is this, and the second order energy correction is this, is false. Okay, so they are asking about all these things, that your zeroth order energy correction, first order energy correction, and your second order energy correction. They are asking about all these three, and they are asking that this should be false. Okay, which statement is false? Always it should be false. So that's what they are trying to ask you. Now fine, so it says you have different points over here. So the first point says that the energy is an average value of perturbation operator with respect to the ground state of the zeroth order Hamiltonian. This is for the zeroth order energy, right? So this is for the first order energy. So first order energy is the average value of perturbation operator with respect to the ground state of the zeroth order Hamiltonian, and that's true. Why? Because for the first order, if you remember, this is what we write, right? We write it like this. So we have like psi star h psi, right, and d tau. So this is actually, we are calculating the average value of it. So the first statement is correct. It's not false. It's true. Okay. The second one says that your first order energy correction necessarily will be negative. So it has to be negative. But that is not the correct case. We have seen that the first order energy correction can become zero also, and it was zero in the case of simple harmonic oscillator. Remember, so it is not necessarily negative. So this is false. Okay, this statement is false. So this is wrong statement. Third one says that second order energy is necessarily negative. That is true. Why? Because for second order energy correction, we write it like this. So we have this. So we have like okay, so we have this, right? So we have psi m, and then we have h psi n, right? And in the denominator you have you have En minus Em, and we know that Em is the energy for the higher energy level, En is the energy for the lower energy level, right? So if you subtract if you subtract higher energy value from the lower energy value, you will get negative in the denominator, and then in the numerator you have a square value. So that means in the numerator, whatsoever you will get a positive term from there, right? So in the denominator you are going to get negative term. So that means the second order energy correction is necessarily negative. So that is also true statement. The fourth statement says that E0 0 and E1 0 is an upper bound to the exact ground state energy. That is also true. So this zeroth order energy correction and first order energy correction, if you add both of them, it gives you the upper bound to the exact ground state energy. So your point 1, 3 and 4, these are correct. Your point 2 is wrong. So in the question they were asking that which of these statement is false. So actually your statement number 2 is false, and this becomes your correct choice. So like this you can easily answer out and you can score 4 marks over it, right? So it was just a statement based question. You don't have to do much. You are like you guys are paying attention to that, right? That in the second order energy correction, they are not asking you to solve anything or to do mathematics and all. They have just given you some statement. They have just given you certain conditions. You just have to check that whether your given condition is satisfied by that or not. And that's all you are going to get the answer, right? So this is how you can score 4 marks, and this is how the question has to be done. Let's take some more question and let's try to solve them. Okay, so let's take the last question for this particular video. And this question was asked in CSIR December 2016. Okay, so the question was actually asked in your CSIR December 2016 exam, and it was asked for 4 marks, right? So as you can see, all the questions from perturbation theorem which I have taken till now, they all were of 4 marks, right? So let's try to solve this up. This question says that the ground state of the certain system with energy epsilon naught is subjected to perturbation V. Okay, so we are doing certain perturbation V over here, yielding a first order energy correction as epsilon 1. So epsilon 1 is the first order energy correction which you are getting. And if E naught, capital E naught, is the true ground state energy for the perturbed system, then the inequality that will always hold. So remember few things over here which are given to you. First thing is that E naught is what is your true ground state energy, right? So this is what it is given to you. Epsilon naught is the ground state perturbation, okay, perturbation which has been done. Although ground state perturbation is not that important, but yeah, in the ground state also there is certain inequality which is given to you. Okay, so this is what your ground state perturbation tells you. And your epsilon 1 is is the first order perturbation or first order correction. Okay, so that's what it is. So it's a first order correction. So what does this mean? What does that, which inequality will hold? So I have already told you that what is this perturbed part. What I have told you, that always we have certain energy. Let's say if E dash is the energy, so that will be we will be having E naught plus delta E, and this delta E is the perturbed energy, right? And E naught is your actual or the true ground state energy. So in the perturbed energy level, or in the energy which we are calculating, we'll get certain more energy, certain little higher energy than the actual or true ground state energy, that will be given by delta E, right? So that means always whatever we are going to calculate will be either greater than or equal to whatever the true value is. Okay, try to understand it once again, that whatever we will be whatever we are going to do, whatever we are going to calculate, whatever we are going to find out from the perturbation theorem, so that part or that energy will always be greater than or equal to the actual energy, because you are just trying to find out this extra part of it, right? So that's why whatever energy you are calculating, that will be having certain extra part than the actual energy, so that will be little more that will be greater than or equal to your actual energy. So by that you can say that your option number 4 should be your correct option, which include both your energy for the perturbation as well as your your first order energy correction. Okay, so the sum of both of them should be always greater than or equal to your the actual or the true ground state energy. Fine. So that's how your correct option should be your option number 4, and like that you can easily solve this particular question. So that's all for this particular video, guys. I hope you guys like this video, and if you like this video, give it a like, subscribe to this channel if you are new to it, and you can comment down in the comment section whatever you want to ask, anything related to these things. I hope this video was helpful to you, and I will try to make a separate video on just problem solving from the quantum chemistry. I have covered both variation theorem as well as your perturbation theorem, and I hope this was very helpful for you. So thank you so much for watching this video. Have a great day. Bye bye.